So now we're going to go actually back to a little bit of more biological chemistry and look at how intermolecular forces affect that. Now we mentioned the other day in class that DNA is affected by intermolecular forces, is how those molecules are held together, how we get that double helix. But we also see that these intermolecular forces affect the properties of lipids and also look at trans fats, which again is the big buzzword in nutrition. So when we look at fats and oils, the only difference between fats and oils is one's a solid and one's a liquid. We talked about this when we talked about saturated versus unsaturated. Here on the left, we see we have one single double bond here, one mono unsaturated, the whole big triacylglycerol or triglyceride. And over here we have several double bonds. So we have multiple points of bends, multiple places where these molecules are bending. And just like we saw with our alkanes, the more points of interaction, the stronger the intermolecular forces. And that's what we see here. There's more places for these molecules to interact with one another. They're also going to be interacting with other of these triglycerides or triacylglycerols of other molecules of those, other units of those, and these tails are all very close together, and as a result, this is going to be a solid. That's why it is called a fat, because it's something that's a solid. If I look at an oil, that just means it's in the liquid phase, and that's really the only difference between fats and oils is one's a solid and one is a liquid. And so here we look at oil where we have multiple double bonds. We see that the tails are farther apart. They're not interacting as much with each other. They're also not going to interact as much with other triacylglycerols. And so as a result, this is in the liquid phase because it has a lower intermolecular forces, less interactions between these fatty tails, these fatty acid tails, and therefore weaker intermolecular forces, a lower melting point, easier to get into the gas phase. If we look at the fat, the tails are closer together, stronger intermolecular forces, stronger attractive forces between these tails, and as a result it has a higher melting point, so it's going to be a solid and put to a higher temperature than what we see for the oils. So let's look at the structures of these molecules. These are called triacylglycerols or triglycerides. If you've had blood work done, you probably had your triglycerides checked at some point. What we see is that we have this glycerol backbone, which is 3 carbons. And glycerol, if we just show the structure of glycerol, we have 3 carbons, each with an OH group attached. And I'm not going to fill in all the hydrogens. I'll just put some dashed lines in here to represent the hydrogens. But this is a glycerol molecule that I've drawn in here. And what we've done is basically taken off one of these hydrogens on each of the oxygens and put on this fatty acid chain. And we've connected that to there. And this is happening in our body. Actually, body stores extra fat as these triacylglycerols. And so we have the tri because we have 3. It's the glycerol because we have our glycerol backbone, this part of the molecule. And the acyl is telling us something about the bond that forms between the glycerol and the carboxylate salt. So what happens? How do we get margarine? Because margarine is actually partially hydrogenated vegetable oil. And you'll see this label on a lot of things. All that means is, just like we talked about hydrogenation with alkenes, we can see that we have our alkenes add hydrogen in the presence of a catalyst, and we took away our double bond and we added 2 hydrogens. We can do the same thing with margarine, which would normally be in the liquid phase. So we take vegetable oil that has multiple double bonds, and we hydrogenate some of them, not all of them, because we don't want it to be like a saturated fat where we have lots of interactions between those tails of the molecules and between neighboring molecules, but we want to get it to something that is more solid because for baking or cooking or a variety of reasons, sometimes it's just easier to transport, whatever we're looking for, we want something that's more in the solid state. And so by partially hydrogenating those oil molecules, what we find is that we've increased the intermolecular forces between those tails and between neighboring molecules. We've raised the melting point, and so now it is a solid, and now we have something that has a very different consistency than the liquid oil. So if I need to bake something with a solid, then I can use that partially hydrogenated margarine. Now there's some other issues that go along with that dealing with trans fats, and we talked a little bit about them before about the way they are produced. Another place we see that intermolecular forces, these attractive forces playing a role, is in the cell membrane. And the cell membranes have a pretty important job. They've got to kind of control, they're the gatekeepers for everything coming in and out of the cell. And so being able to kind of regulate that is important, and intermolecular forces play a role in that regulation. So when we look at cell membranes, we see something that looks similar to what we saw for our triglycerides or triacylglycerols. We see that we have our glycerol backbone here. We have our 3 carbons that each had our OHs attached to them. Now we have 2 fatty acid tails, but we also have this phosphate head, and we call this a phospholipid molecule because it's kind of like a lipid in that it has the glycerol backbone. It has 2 fatty acid tails, but it's not a lipid because it doesn't have the 3 fatty acid tails. However, it does have this phosphate group, so we give it the name phospholipid. And this is actually what cell membranes are made of, is this phospholipids, and we'll actually see the layers that form of these molecules. So when we look at the cell membrane, what I actually see are the layers here. I have a phospholipid bilayer. Remember, bi just means 2, so 2 layers of phospholipids. Remember, our body is a very aqueous environment, and that's true outside the cell as well as inside the cell. And so these hydrophilic heads of these phospholipid bilayers are actually on the exterior of the cell and on the interior of the cell. What's in the middle is this nonpolar, these long tails that are attached to that glycerol backbone. Much like we saw with the carboxylate salts with our soaps, we saw that when we put a soap in water, all of the nonpolar parts kind of connected to one another and interacted with one another and tried to avoid that aqueous environment outside of that little bitty unit. And the cell membranes are no different. We have our polar region that's interacting with the outside of the cell and the inside of the cell, and we have this non-polar region here in the middle. So when we look at our cell membrane, what we see is that these are actually called semi-permeable membranes. And so what happens is that permeable means that things can go in and out. Semi-permeable means that some things can go in and out. And the cell has to control nutrients coming in and waste going out. And it has to control the flow of that. And it does that by a couple of different things. So the first thing we see is our phospholipid bilayer. So here we see our polar regions here on the outside and inside of the cell. In the middle, we see our non-polar regions, those fatty acid tails that are on that phospholipid. So we have our hydrophilic region and our hydrophobic region. We see that we have some molecules kind of embedded in the surface. These are actually cholesterol molecules, so we do need cholesterol in our diet. We don't ever want to go to a situation where we have no cholesterol. It's used in cell membranes. It's also used as a building block for other things as well. So we have our polar and nonpolar region that correspond to the hydrophilic and the hydrophobic region. And what we also see is that there's a variety of proteins and carbohydrates kind of stuck throughout this phospholipid bilayer, throughout this cell membrane, because what we're looking at here is that these channels allow things to pass in and out. Based on the properties of these channels, we can get polar substances to flow through. It's going to be a little bit harder for a polar substance to come through this non-polar region here in the middle because there's going to be repelling happening between those molecules. Here we have these proteins. They act as basically little channels, kind of like little tubes or openings that let these substances in and out of the cell. Now it seems kind of odd that we're including steroids here, but steroids are actually classified as a lipid because they were classified based more on properties of the substance rather than structural features. And so what we see is that a steroid is always going to contain these 4 fused rings. We've got 3 hexanes and the 1 pentane, and they'll always be in this same kind of general layout. You're going to see numbering, and you may see some problems on mastering that refer to the numbering here and asking you which carbon is attached to what and things like that. You can absolutely refer to this numbering system, refer to this image that's in your book as well. I will not expect you to know how to number these steroid molecules on the exam. If you should know it, I would also give you something about the numbering, but I don't expect you to know that. What I want you to be able to do is recognize that we have these 4 fused rings together. And so these steroids, these also are the basis for a lot of other compounds and a lot of things that our body needs to build. It needs these steroid kind of units, this nucleus, this kind of central part of the molecule. And so when we see steroids, we actually see lots of different functional groups or side groups coming off at a variety of points in the structure. So cholesterol is actually an example of a steroid. We mentioned we saw this in the cell membrane. We see our 4 fused rings. We have 3 6-membered rings and 1 5-membered rings. It doesn't matter that there's a double bond. You're going to see some of those throughout these different structures. But what we see is that we have an OH group over here. We have a methyl group, another methyl group. We have this long carbon chain, and this is actually the structure of cholesterol. And so this is going to be the same kind of basis for a lot of the steroids and a lot of hormones that are produced in our body, is this backbone of cholesterol. So if we don't have that, then we need to actually consume some of that. Our body can make a little bit, but we actually need to consume some cholesterol in order for our body to use it kind of as a building block for other substances. So cholesterol is found in cell membranes. It's also found in brain and nerve tissue. So also another important reason that we need some cholesterol. The problem is that we have too much cholesterol. I would suspect that very few people in the United States have an issue with too little cholesterol. And so the primary use is it's starting material for other steroids. So we've got to build other steroids. So it makes this kind of nice, not a blank slate, but a fairly simple molecule that the body can then use to build other things. And so we do make a little bit of it on our own. Okay, so we see we've got a little bit of it on our own, synthesized in the liver. We also get it from animal products. So if you're a vegetarian or vegan, then you're going to have to worry about where you're getting that from. It can be found in other sources, but these are kind of the main 2 sources. And so when we look at excess cholesterol, which is a far more serious problem in the U.S. than not enough cholesterol, this is where we end up with plaque in our arteries, and so that buildup. So excess cholesterol, our body doesn't know what to do with it, so it ends up kind of basically sticking to the arteries, and that's where we end up with problems like heart attacks because the blood can't flow properly. So this is the end of chapter 7. And I know we talked about a lot of different things in chapter 7, but they all kind of come back to the topic of intermolecular forces, of looking at how molecules interact, or in the case of gases, how they don't interact with each other. And as a result, we can start to predict properties like melting point and boiling point and solubility. And it's not that we can look at a molecule and say, oh, well, of course the boiling point is 72 degrees Celsius. I'm not going to know that degree of information, but what I am going to know is that one molecule has a lower melting point than another molecule, or has a higher boiling point than another molecule, or it's more soluble in water than some other compound. It's all about kind of these relative assessments, these very qualitative assessments, and being able to rank substances in some order of increasing trend. As always, if you have questions, please feel free to come see me during office hours or post on Piazza, and I'll be happy to answer your questions.